What is going on, everybody? Welcome back to our channel. You are watching Introduction to Graph Theory. In this video we are going to look at trees, spanning trees, and also we'll be looking at how we can create minimal spanning tree by using Kruskal algorithm. So let's get started.
A tree is a connected and a simple graph with no cycles, also known as acyclic. A simple graph, remember, was the one with no self loops and no multiple edges. So in a given graph, the line in the red are multiple edges between vertices, and also some of them are creating a loop. By simply removing them, we end up making a tree graph. A simple theorem for that is for any connected simple graph G with n vertices and m edges, the total vertices will be either equal to or less than the total number of edges plus 1. In the given tree graph, total vertices equals 7, edges are 6, so 7 is equal to 6 plus 1. So a tree always has n is equal to m plus 1. So summarizing the properties of a tree graph, the first one is a graph G is a tree if G is connected and there are no cycles. A graph G is connected and number of vertices is equal to number of edges plus 1. Same goes for acyclic. There exists a unique path between every two nodes, and every edge is a cut edge, which means that by removing an edge, we will end up disconnecting the graph into two components. Also, adding another edge creates a cycle. A spanning tree is a tree which is a subgraph of G containing all the vertices of G. More formally, it can be written as T, which is a subset of graph G if and only if all of the vertices of the spanning tree is equal to all of the vertices in the original graph G. So on the right, we have the graph G. In order to make the spanning tree of this graph, we make it simple and remove all the multiple edges and loops. We will end up like this, which has all of the vertices of the original graph G. A minimum spanning tree is a tree with minimal total weights. To make a minimum spanning tree, we will follow the Kruskal algorithm, where we will start by selecting the minimum weighted edge and adding it into a set S. Choose the next minimum weighted edge such that it is acyclic with the existing edges of the spanning tree, and it does not necessarily have to be connected. Finally, stop when there exists no such edge. Again, confusing, right? So let us take an example. So in the given example graph, we will start by selecting the minimum weighted edge, which is highlighted in black. Next, selecting the next minimum weighted edge, but make sure that it does not make a cycle, highlighted as black. Going on, the next one is with 2, then the next one is 3, but we won't be selecting it because it is making a cycle between V6, V5, and V8. So we will skip that, and the next one is 4. Next is 5, then the next one is 6, but we won't select that because again it's making a cycle. Next is 7, then we have 8 and 9 both making cycle, we will skip that. Then we will select 10, then 14 and 11 again are making cycle, so we will skip that. So we end up finding no more edges greater than 10 that makes a tree. And this graph has all the vertices of the original graph, and if we get rid of all unwanted edges, we have created a minimum spanning tree. So let us prove whether if this fulfills all the properties of a tree. So we are sure that the resultant graph is the subgraph of G such that it has minimum weights. And let's see if it follows n is equal to m plus 1. Total number of nodes are 8. Edges are 7 plus 1 equals 8. Every edge is a cut edge. So if we remove any edge, we will end up in two components of the graph, and hence disconnecting the graph. Unique path between every node. Adding another node creates a cycle. That is also true.
That is all for this video. I hope it was informative for you guys. If it was, please don't forget to like, share, and do subscribe if you are new to this channel. This is going to keep us motivated to bring such useful stuff to you guys in the future. So, till the next video on graph theory, I will see you guys in the next one. Take care. Bye.